Welcome to the Explainer. Today, we're diving into the art of code. We're going to pull back the curtain and look at the hidden blueprint that turns a simple idea into the complex, powerful apps we all rely on every single day. And that really is the central question, isn't it? I mean, think about your favorite app. Every single button, every feature, every piece of data, it all has to work together perfectly. Without a rock-solid plan, trying to build something that complex would just be, well, chaos. You'd never end up with the stable, reliable software we expect.
So what's the secret? Well, it's not some wild flash of genius or a lucky guess. It's actually a disciplined, methodical process. You know, just like an architect would never ever dream of building a skyscraper without a detailed blueprint, a programmer needs a solid plan before they can even think about building a program.
And in the world of software, that blueprint has a name: the Program Development Lifecycle, or PDLC for short. The best way to think about it is as a roadmap. It's the guide that brings order to all that potential chaos and makes sure the final product, actually works.
So, the PDLC breaks this whole journey down into 5 clear phases. And trust me, skipping even one of these is a recipe for total disaster. First, you have to really truly understand the problem. Then you design a solution, then you write the code, then you hunt down every single error you can find, and only then do you release it and keep it running for your users. Now that design phase is absolutely crucial. Before a single line of code gets written, developers use specific tools to map everything out. They might use a flowchart to see the step-by-step logic, or something called pseudocode, which is basically writing out the program's logic in plain English. It's all about having that detailed plan before you even touch the keyboard.
Of course, no plan is perfect, right? And that brings us to a huge step: debugging. This is just the process of finding and fixing all the little errors and flaws, which in the programming world we call bugs.
And what's so cool is where that term actually comes from. The very first computer bug was literally a bug. I'm not kidding. Back in 1945, a moth got stuck in a relay inside a massive computer and caused the whole thing to fail. The engineers actually found the moth and taped it into their logbook. Okay, so you've got your blueprint and you're ready to hunt for bugs. Now you need the actual tools to build the thing. And in software development, those tools are programming languages.
And man, have these languages evolved. The very first computers could only understand pure ones and zeros. That's it. But over the decades, we developed what are called high-level languages that use words we can actually understand, like if or print. This made it so much easier for humans to tell computers what to do. So to see how these modern tools really work, let's zoom in on a true giant, one of the most influential programming languages ever created: Java. Java's story kicks off in the early 90s. And the funny thing is, the team that created it wasn't even trying to build something for big computers. They were actually trying to write software for consumer electronics, like interactive television sets. And that specific challenge led them to create Java's first superpower, being platform independent. They had this simple but powerful goal: write once, run anywhere. This was a total game changer, because before Java, developers often had to completely rewrite their code for every different operating system. It was a huge pain. So, how does this magic work? Well, a developer writes their code in a Java file. Then, a special program called a compiler translates it. But here's the trick. It doesn't translate it into code for a specific machine. Instead, it creates this intermediate universal format called bytecode. And this is the brilliant part. That single bytecode file can be sent to any computer: Windows, Mac, Linux, it doesn't matter. As long as that machine has a piece of software called a Java Virtual Machine, or JVM, it can understand and run that bytecode. One program running literally everywhere. Java's other superpower is all about how it's structured. It's built on a concept called object-oriented programming, or OOP, and really, it's just a powerful way of organizing code that's designed to mirror how we think about things in the real world. One of the core ideas in OOP is something called encapsulation. The idea is actually pretty simple. You bundle the data together with the code that works on that data, all in one self-contained package. This keeps everything organized, and really importantly, it protects that data from being accidentally changed or misused. The perfect way to think about this is a medical capsule. You know how it holds all the different ingredients together in one little package, protecting them from the outside? Well, in programming, an object does the exact same thing. It encapsulates all its data and functions into one neat, protected unit.
And this brings us to probably the most important idea in object-oriented programming, the difference between a class and an object. Just think of the class as the architect's blueprint. It defines all the rules, all the features. The object, on the other hand, is the actual house you build from that blueprint. It's the real, tangible thing you can actually use.
Here's a great example. You could create a class called Animal. This blueprint would define general things like has legs or makes a sound. But from that single animal blueprint, you can create lots of different unique objects. A lion object, a zebra object, an elephant object. Same blueprint, totally different results.
All right, so let's bring this all home. We've seen how modern software isn't just one thing, but a combination of a structured process and a really powerful language. So if there's one thing to take away from all this, it's this. Creating great software isn't magic. It never has been. It is always the product of two things working together. A disciplined process, like the PLDC, to manage all the complexity, and powerful tools, like Java's object-oriented approach, to build things efficiently and securely. And that leaves us with a pretty fascinating question for the future. For decades, software has been built on human logic and these very structured processes. But as AI gets better and better at writing its own code, you have to wonder, what will the blueprints of tomorrow even look like? Will we need them at all?